Hey Chem Kids, Campbell here. In our third video on Chapter 5, we're going to talk about electron configuration. What an electron configuration is the distribution of an atom's electrons in all those levels and sublevels and orbitals that we talked about in the previous video. Now, in order to fill these up, we need to know, where do we start? Well, we have a principle. It's called Aufbau's principle. And it tells us that electrons are added to that lowest energy level possible. And we fill in there until we run out of electrons. So we start at the bottom, which would be our n equals 1, or that principal quantum number 1, or the lowest energy level. And we start filling upwards. So we start at the bottom and we go up. Well, how many electrons does an atom have? Well, do you remember from last unit? We need our periodic table. Remember that the number of electrons in a neutral atom is the same as the atomic number. And remember, the atomic number is the number on the top left corner of the little box with the element in it on your periodic table. So if you don't have your periodic table out, get it out. You're going to need it. A couple things to remind you about from the previous video is that anytime we put sublevels in an energy level, remember that the number of sublevels is equal to the energy level number. So remember, level 1 can only have 1, that's the S. Level 2 can have 2, that's the S and P, and 3 can have 3, and 4 can have 4. And you also have to remember how many types of orbitals each has and how many maximum electrons, right? Because if we're filling electrons, we need to know how many we can put in to each of these sublevels. So an S, remember, is only one orbital, so it can only hold 2. So once we've put 2 electrons in an S level, it's full, and we have to go to the next higher level. So if we're filling a P has 3 types, so that means we can put 6. So once we put 6 electrons into a p orbital, we need to move to the next level. D can hold 10, F can hold 14. So those numbers that we learned about in our last video, we're going to need them for this one. Now, electrons, like I said, they fill lowest to highest, lowest energy level first, and we fill upwards, but there's a problem. When we hit those d orbitals, they're actually higher in energy than an s orbital. What? So what that means is once we get to the third row, right, the third row is the first row that could have a d orbital. Well, instead of going right from 3p to 3d, we actually go to 4s first. So 4s fills before 3d. What? So, but I have help for you. If we make a diagonal diagram of all of those energy levels and orbitals, and we make little diagonal lines, we can actually fill it correctly. So if I follow these lines, and I do this as I fill up each orbital with electrons, then I will get that filling order right. And you can see here, when I hit 3p, I don't go to 3d, I actually go to 4s before I go to 3d. And same thing with 4D. I go to 5s before I go to 4D. So what I want you to do is make a diagonal diagram, because we're going to be using this as we fill electrons. So this is how I make my diagonal diagram. On the periodic table, you'll notice that there are 7 rows. So what I do is I write 1, 2, 3, 4, 5, 6, 7. If the lowest level in an energy level, the lowest orbital type is an S. So I write 1s, and all of them can have 1 orbital, right? So I just write s all the way down. Now, 1 can only have s, right? Energy level equals the number of orbitals. But 2 can have 2. So 2 also has a p. So I'm going to also write 2p. And if level 2 can have a p, that means everything below it can too. So we have a 3p, a 4p, a 5p, a 6p, and a 7p. Now, once I get to p in the second level, I'm done, right? 2 can only have 2, but 3 can have the d. So we're going to add 3d. And if 3 can have d, then so can 4, 5, 6, and 7. So 4d, 5d, 6d, 7d. 4 can have an f. So 4F, 5F, 6F, 7F. Now 5 could have a G, but we don't have any elements that have that many electrons, so we can stop when we get to the F's. Now we just make diagonal lines. So we fill a 1s, then we go to 2s, then we go to 2p, 3s, 3p, 4s, 3d, 4p, 5s. So we just make these diagonal lines through our numbers just like that. So let's see, how do we use this? So let's pick an easy one. Let's start with beryllium. If you find beryllium on your periodic table, you'll see that it's over here. Its atomic number is number 4, which means it has 4 electrons. All right, so remember we start at the bottom, which lowest energy level, so I guess it's the top of our diagram. We're going to start at 1s. So what I'm going to do is I'm going to write down 1, that's the energy level. S is the sublevel. And remember, an S can hold 2 electrons, and I have 4, so we're going to put 2 in here. Once I put 2 in there, it's full. It can't take any more, so we need to go to the next level. So our next level, if we follow our line, takes us to 2s. Now, I just used 2 electrons, so I have 2 left. And that's great because an s orbital can have 2. So we're going to put a 2 here. Notice I write the electrons as a power. Not that I'm squaring the s orbital or anything, but that's how I denote that I have 2 electrons in the s orbital, and that s orbital is in the second energy level. I just used 2. I have none left. So this is the electron configuration of beryllium. See, that's not too bad. I mean, the most work is really filling out that diagonal diagram. Let's try 2 more. What I want you to do is on your periodic table, find magnesium and find vanadium and find the number of electrons. Then pause the video and see if you can get the right electron configuration. Well, if you look for magnesium, you'll see it here in the 3rd row. Its atomic number is 12. So that means that magnesium has 12 electrons. So I'm going to write that down so we can keep track of it. So we always start in the 1s orbital, and the s orbital can hold 2 electrons. All right, 2 electrons, I got that. So I got 10 left. So let's keep going. I go to the next one, and that's the 2s, and an s orbital can hold 2, so we're going to put 2 right there. Well, I just used another 2. That means I have 8 electrons to go. So let's keep going. After the 2s, we get to 2p. So I'm going to write down 2p. And remember that there's 3 types of p, which means it can hold a maximum of 6 electrons. Do I have 6 electrons left? Heck yeah, I have 8. So we're going to fill up our p orbital by putting 6 electrons in there. That gives me 2 left. So let's keep going. After our 2p, we get to 3s. So 3s, we're going to write down 3s, and an s orbital can hold 2. And I used 2. Now I have none left. Did you get that? 1s2, 2s2, 2p6, 3s2? I hope so. All right, let's see how we did on vanadium. Now, vanadium, it actually took me a while to find vanadium. Vanadium is one of our transition elements. It's right here. It happens to be number 23. So that means it has 23 electrons. All right. Well, starting in the bottom, all right, we have 1s2. After 1s2, we get to 2s2. All right, that's 4 electrons. I got more than that, so let's keep going. 2p. 2p can hold 6 maximum. So how many have I used so far? 6, 7, 8, 9, 10. I've used 10 electrons so far. That means I have 13 to go. Whew, I still got some work to do here. All right, after 2p, we follow our line down, right? And we get to 3s. And s can hold 2. So let's get rid of 2 of those. I have 11 electrons to go. After 3s, we come back up here to the 3p. So we're at 3p. P can hold 6. And I still have definitely 6 left. So let's take off 6 from here. So what do we got? 5 left? Can I do math? Sometimes I can't do math. After our 3p, we keep going down here. We get to 4s. An s orbital, doesn't matter what level it's on, can only hold 2. Subtract 2, that gives us 3 more. And so that means I got to keep going. After 4s, now we get to 3d. I know it seems weird, but a 3d orbital has more energy than a 4s. Now remember, a d, there's 5 types. That makes it can hold 10 electrons. But I'm not going to put a 10 up there because I don't have 10 left. I only have 3 left. So we're going to put a 3 up there. So it has 3 electrons in the 3d orbital. And now I'm done. And if I want to check, make sure I didn't mess up, go back and add. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 3 is 23. Woo! 23 electrons. Vanadium's number 23. Check. Now, you may be wondering, are there any other ways to do this? Well, there's another method that uses the periodic table. So if we take a look at your periodic table, notice that your periodic table has 7 rows. And there are, in this periodic table, what we call 4 major blocks. So if we take a look at those blocks, the first 2 here, right, these stick out. This is the S block. This block here we call the P block. This here, the transition elements here, this is the D block. And down here, this is the F block. Now, this is significant, and I'm going to tell you why. If you take a look, right, in the S block, these first 2 columns here, remember that an S orbital can hold, or an S sublevel can hold 2 electrons. And notice there are 2 columns. If we skip over to the P block, right, a P can hold 6 electrons. And if you count 1, 2, 3, 4, 5, 6, there are 6 columns. Cool. And if we go to our transition elements here, right, that's the D block, and it has 10 columns. And down here, the inner transition elements, if we count all the way across, there are 14 columns. Guess what? That's the F block, right? F block, D block, P block, S block. And each of those blocks has the same number of columns as the maximum number of electrons that each sublevel can hold. So how do we use this? Well, we're going to start filling our electrons and just move along till we get to the element of interest. But there's one little trick here, and I think it's easiest probably to see it here. If we actually put the F block in where it belongs, it goes into the 6th row. And remember I said that the inner transition, these are the F and these are the D, right? So if we look at 6S, right, we go to 6S2 and then we hit this F block. Now if you look here, we go 6S on our diagonal diagram, and after that we get to 4F. So in fact, this is a 4F sublevel. So even though it is in column 6, this is 4F. So when we use this method, we need to make sure we take the row number and subtract 2 for F orbitals. And for our D orbital, right, after that 4F2, I get to 5D. So D, I have to subtract 1, because even though this is in the 6th row, it is the 5th D orbital, or sublevel. Now, let's go and see how we use this. That's the important part, right? And let's do germanium. If you look at your periodic table, you'll find germanium in the 4th row, in the 2nd block of the P block, that 2nd column. So what we do is we literally just fill electrons and we go in sequential order until we meet germanium. So we start off the beginning. That's 1s2. Helium is really here from an S standpoint. We filled up the S, we go to our next row, which is 2s2, and notice I can go all the way across, and I'm still in the 2nd column. Now I'm in the P block. I haven't gotten to germanium yet, so I'm going to put 6 electrons, so that's 2p6. I now go to my next column here, or my next row, which is the 3rd row, and I fill 3s2. Still going, I haven't reached germanium yet, so I go to the next one, which is 3p6. Still going, still filling electrons. I go to my next row, which is the 4th energy level, and I'm in the S block, and I have 2, so I'm going to put 2 in there. And now I have to go into a D block. Now remember, we subtract 1 from the row number, so this is the 3D, right? 3D fills after 4S. And I fill all the way across because I haven't reached germanium yet. So that's 10. So I put 3D10 because I just filled in 10 boxes. And I keep going. I got 2 more to go. So I'm in the 4th row in the P block now, and I'm in the 2nd spot, which makes this 4P2. Pretty cool, huh? We'll talk some more about this in class. So, see you in class.